We're going to start this lecture on elementary elasticity, which is a really fundamental concept when it comes to structural mechanics or really structural engineering in general. Since structural engineering is essentially the combination of using equilibrium and statics, so think free body diagrams, some of the forces equal zero, some of the moments equal zero, combined with mechanics of materials. And elementary elasticity is really the basis of this mechanics of materials. And so when I say mechanics, you can think stress and strain. So both of these terms get used in sort of popular everyday speech. So stress, when you're under a lot of stress, it feels like you've got a bunch of things weighing down on you. You feel stretched. So that might be a strain. Strain, you feel like, oh man, I've really, I'm stretched thin. And that's what you'll see as we go through this, that stress is really related to, forces, and strains are really related to deformation, so that stretching thin part. But both of these really, and sort of elementary elasticity in itself, really comes down to one key concept, and that's that external forces applied to a structure generate internal actions. And we can think of this as Newton's third law of motion. So for every action, there's an equal and opposite reaction. And this should make, good intuitive sense to you. If you've been around the world for, a few decades now, you've pushed on things and they haven't just given way. I'm sure that almost all of you have stretched a rubber band, and then you can feel that there's some tendency for it to want to pull back. So you're pulling against that's some elastic force which is in there, and also it stretches, it strains, and those are the concepts that we're going to explore in this section of elementary elasticity. And the way we're going to do this is I'm going to introduce these things sort of at a conceptual level, and then we'll dive into some of the math and some of the more heavy derivations. And so my philosophy when it comes to learning most anything is to understand the concepts behind it and get a good sort of mental picture, mental map. And from there, the math will sort of helps reinforce that. And while the math is important, it's really that innate understanding is what makes you a good engineer, because it gives you that feeling that something's right or something's not. Or where I find that mathematics, if you focus too heavily upon there, you're going to get sort of caught up and easily confused. So with that, what we're going to do is we're going to look at the first part of this elementary elasticity, which is really stress. So if we're looking at stress, let's just start with an example. So for our example, what we have is this member. It's a prismatic member. We're going to assume that it's square, and it has some height. The height, not important. But on this member, it has a compression load, which is acting right at the centroid C. And it's got a load P. Because it's an equilibrium, it has an equal and opposite load P down here, also acting through the centroid. And it has area, it's just going to equal A. So what we want to find out is that, all right, so we know how to deal with this project now from a statics point of view, where we can sum the forces in the y and we can solve for any unknowns, and you already have lots of practice with that. So if we want to look at, well, really this key concept, we know the external forces part. Well, what's the internal action? So that's all we're doing here is we're relating external forces to internal actions. Well, the best way that I know how to do that is to take a free body diagram. And remember, when we cut through an element, we expose whatever forces are on the inside, what those actions are on the inside. So let's take our free body diagram, and just take a cut right through the middle. So that's our free body diagram cut. And we'll draw it over here. So we expose the top, and that's our element. So we know that we still have this force P on the bottom because we didn't cut through there. But in the middle, what we've essentially done is we've exposed all of those little internal actions, these little tiny, minute forces. And we know from statics, so these are internal actions. We know from statics if we sum the forces in the y, it has to equal 0. So we know that P has to equal the sum of the internal actions. So all of that has to sum up to equal this. So how do we know what the value of these little tiny arrows is? Well, what we can do is we can start with an assumption. So let's just assume that they're distributed evenly. All right, so if they're distributed evenly over area A, well, then we know that if we take our equilibrium, where if P is our external force, well, if all of these are distributed evenly over an area, we know that if we sum them all up, when we basically multiply, each individual one by that area, we get some force. So essentially, our external force equals our internal actions multiplied by the area. All right, that makes sense. So if all of these are even, if we sum all of them up, it's the same as you take the resultant of all of them multiplied by the area. So it's similar to like distributed load. So we're familiar with that already. Well, let's rearrange this equation a little bit. And because really we want to know so we know our external force, we know our area, we want to find out what these internal actions are. So we call our internal actions equals our external force divided by the area. And in essence, all we're saying is this internal actions is really a stress. So a stress is just an applied force divided by the area which you're applying it over. So you can think of it like a force density. And you'll notice that, if we look at some units for this, so force, say we call that newtons, and an area, millimeters squared, equals MPa. It's the same as a pressure. So stresses and pressures are related. We have the same units, and it's much the same thing. So think of it like a force density is all stress is doing. But this is essentially our governing conceptual equation for what a stress is. It's just an applied force over the area that you're applying that force. So area, we'll say applied. And if we think about this, for the same area, bigger force, bigger stress. Same force over a small area, bigger stress. And then the way that this gets commonly written is because it's a lot of work to write out stress and all that. So we give stress the Greek letter sigma. So it looks a bit like a tape measure. So sigma equals P over A. And this, and what we've drawn up here in our example, is an example of direct stress. And you might also think of direct stress as axial stress. So that's cool, that makes some sense. I mean, if we look at our little example up here, we've got our forces, compressing down some area, P over A. Cool. This is easy for us to wrap our head around and understand. One last thing before we start looking at some examples and about why do we care about stress is our sign convention. So our sign convention is tension equals positive. And compression is negative. And that's there's nothing innately unique about that. That's simply just how we as a structural engineering community have decided that we should talk about stresses. Where if we have a pulling stress, it's positive, and if we have a pushing stress, it's negative.